mass and density. And the first thing we want to discuss is, well, mention maybe, is when we are in the constant case. Okay, so when constant, and this is an important part, we have the following, that mass equals, it's density times volume. Density times volume. And the symbols here are frequently M is density, that would be a delta, and then volume. This is when constant. Now, we will consider two cases. And case one is when we have a thin wire okay, and we want to think about this as being one-dimensional. In this case, or in both cases, we consider the density is not constant, and so we have a density function that is delta of x. Maybe I can fit it here. Delta of x, okay? And so we think about this lying along, say, the x-axis, one-dimensional thin wire. And the second case that we consider is, think about a metal plate that's two-dimensional. So a metal plate. This is two-dimensional, and we do not consider all generalities of a two-dimensional metal plate. We have, in this case, the density function, again, is delta of x. And this is an important thing to note, is that for our two-dimensional case, I'll put a little star, is that the density does not depend on y. On y, but only the variable x. Only the variable x. If we had a density function that depended on y, well, we would need Calc 3, and that is not this course. Okay, and in both of these situations, in both, whether it is a thin wire or a metal plate, the object is lying between x equals a and x equals b. Okay, so we can't just multiply. We can't just say delta of x times volume. Well, maybe let's discuss units for a minute here. But this here that we know is the case in the constant is really what will help us set up the right calculation and when we have a density function delta of x. So let's talk about units, and I dropped a marker, but it's okay. The units. Primarily, when we talk about mass, we are working metric. We will see the US customary when we get to work, but with mass, it's really a metric calculation for the most part. And let's think about all of the units here. So we have mass. Mass is always in kilograms in the metric system. And this should equal, I'll do this in blue. Oops, well, the equals is in black. This would be density times volume, at least in the constant case, although this is helping us think about units even in the non-constant case. And density is, well, we have two possibilities. It's either kilograms per meter, this is for the one-dimensional case, or it's kilograms per meter squared in the two-dimensional case. And then volume, you might think volume is a three-dimensional thing only, but really when we're talking about something of any dimension, you could have an n-dimensional volume. It just happens when you are in three dimensions, the volume is the volume that you're used to thinking about. So for instance, for a thin wire, the volume is just length. It's a one-dimensional measurement. So this is in meters. And for the metal plate, the two-dimensional volume is just area. This is in meters squared. And you see that if you multiply, at least the units check out, that we always get kilograms for our mass. Okay, so what we're going to do is first we're going to look at the thin wire case, and then we'll look at the metal plate case. Let's consider the first situation, the thin wire, and I will draw a picture. Here is x equals A, x equals B. We have a thin wire that we're supposed to think about as being one-dimensional. Maybe I will shade it in blue. Here's my thin wire. And we have a density function which is delta of x. How are we going to figure out the mass of this wire? Okay, well, just like every other application of the definite integral that we discuss, remind sum, right? So, my tray is a little small. Okay, it's life. Let's subdivide, right? So we subdivide A to B into n subintervals of length delta x, which is b minus a over n, and we make n so large, let's say choose n so large that the density, I'll just say this function, is approximately constant on each subinterval. Oops, no E. Period. Okay, so whatever n is, I will just draw a few things here, like this. So here I have 1, 2, 3, 4, 5, 6, and the 6 in my picture, it's supposed to be equally spaced between A and B. Now delta x, these are all, this here is all this length here, delta x, right? And this density function is approximately constant. So if we want the mass, maybe I should have my partition. So we have A is x0 less than x1 less than x2 all the way out to xn, which is B, okay? And if I want the mass on this segment of wire, that lies on this subinterval, xi minus 1 to xi, well, the density is approximately constant. So this mass here is approximately, we just take, let's see, okay, let's just take delta of xi. That's fine. You could pick either endpoint. You could pick a midpoint. You could pick any point in the subinterval, but this is fine. And then this gives us a density. Then we multiply. For this subinterval, the volume is delta of x. Okay, so this is density. This is for this one-dimensional case. We can check units, right? This is kilograms per meter. This is in meters. We multiply, we get kilograms. So this is the mass over, maybe here's this, xi minus 1 xi, if you can see that. Maybe over that subinterval, okay? So what do? We add them up, and this approximates the total mass. Okay, so then the total mass, maybe I will do it here, the total mass of the wire is approximately the sum I equals 1 to n of delta of xi, and then this other delta of x. Okay. It's sort of two deltas. This one is density. This is delta of x, which is a width, but at least this one's capital, this one's lowercase. Okay. So now we can take a limit as n goes to infinity, or as this delta of x goes to 0, and we see the mass of the wire is an integral. So the total mass of the wire, maybe I will write this below, the total mass of the wire is the integral from a to b of the density dx. Okay, we've seen this in a few examples. We don't actually calculate a Riemann sum unless you want to approximate something. But even that, we could use Simpson's rule, trapezoid rule, or we have other techniques with power series, for instance. But we use the idea, write down what a Riemann sum would be, and then the sum sort of becomes this integral sign when we translate to an integral, and this delta of x becomes the dx when we translate to an integral. Okay, well, so this is for a thin wire. What we see from this discussion is you just integrate the density function from a to b. Okay, well, let's talk about for a moment what happens in the two-dimensional case. That one's a little more interesting, and then we will do a few examples. So now let's consider a metal plate. And we consider this two-dimensional. So let me draw a picture. We have some x equals a, x equals b. And then we have some function up here, y is f of x. And we have some function below, y is g of x, and the metal plate occupies the space in between. And maybe I will shade it here and here. Oops, I went a little bit too far. Here's this endpoint, and all of this is our metal plate. Now, this might take you back to Calc 1, where we're calculating the area between two curves, something like this, and that's actually a very good thing to think about as we start setting up these problems. Okay, now, we're going to do the exact same thing. So we have the same idea as the 1D case, which is we partition A to B, the interval A to B, okay, divide it up. Oh, maybe I should add here delta of x now is the density function. And again, as I said, when I started discussing this, what this means for the metal plate is that, well, here, let me go ahead and subdivide. I will subdivide maybe in green. Is that when we subdivide, we have this little strip here, maybe even, oh, I was doing it on this side. So we have a little rectangle, and then over here, like this. If here's my xi minus 1, xi, this length up here would be delta x. Just like the last example, except we have 2 dimensions. But on these vertical rectangles, the density doesn't change, right? Because it's not a function of y, it's only a function of x. So you take some little x and this whole piece has the same density. Or when we subdivide, we have the same density on these vertical rectangles. This is the case we consider. Okay, so we partition A to B into the same idea as before, n subintervals of equal length, this delta x, I should say, which is b minus a over n. And then, again, we can pick n so large that the density is approximately constant on these rectangles. Okay, so now what would be the mass? Maybe I'll do this in blue. What would be the mass of this chunk of metal plate, which is, well, this rectangle, right? So the mass of the metal plate lying over this region, mass of the plate between, or I'll say over, I'll write it this way, this subinterval, and maybe I should write, just for the sake of completeness, I will write my partition. We have x0 less than x1, etc. This is B. Okay, so the mass of this, well, density times volume. It's subdivided enough such that on this, it's approximately constant. So this would be approximately, we take the density, let's say at xi, okay? But now we have to multiply by the volume. Well, this is two-dimensional volume or area. What's the area here? This is why I said it should take you back to thinking about the area between two curves. The area is, you take upper minus lower, that gives you the height, and then multiply by the width, which is delta x. So we have upper minus the lower times delta x. Okay, so let me write underneath what all this is. This one here is in kilograms per meter squared, and this one here, this is in meters, and this is in meters. So you see, everything works out, and we have a mass, we have kilograms. It's always good in setting up a problem with slices to check your units, because if you left something off, you would know. We wouldn't get kilograms at the end, and this will be even more important when we get to work, which is coming very soon. Okay, so this is the approximate mass over this plate, of the plate lying just over this subinterval, I should say. And so then we could take a sum. The total mass would be approximately, just like in the 1D case, a sum of things that look like this. Or I can just write out in integral form as follows. The total mass of the plate would be an integral from A to B. We have delta of x. We have f of x minus g of x, and then dx. Okay, so this is the mass. This is the one that, as I mentioned, was a little more interesting. This is the mass of, in the two-dimensional case, when we have a plate. And it really comes, both of them come from the Riemann sum. Okay, so let's do an example that came off of final, where it's a setup only, and then we might do a more exciting one where we actually do the integral. Both of my examples will be 2 dimensions because there's a little more to it. In the 1-dimensional case, it's quite straightforward. If you're given a wire, you have an A to B that it lives between, and a density function, you just integrate. But the 2-dimensional case, we have a little bit more work to do, and so my examples will be from that case. And let me see, the first example we will do, as I mentioned, this came off of final, and our goal is to set up, but don't evaluate. So example, set up, but don't evaluate. And then we will do one where we actually evaluate. And okay, sounds good. So we have a plate is enclosed by, we have y equals x squared, and y equals 2 minus x squared. And this has area density delta of x equals 3 to the x. Okay, we want to find an integral that gives the mass. Find an integral that gives the mass. The mass of the plate. Okay. Wonderful. Well, you see, this very much takes us back to the days of area between two curves, because that's what we need to do first. We have two curves. We want the region enclosed by them, and we think about a plate occupying that region. So the first thing we need to do is we need to set these equal to each other to figure out where they intersect. So we have x squared is 2 minus x squared. We get that 2x squared is 2, or x squared is 1. We get that x is, maybe I will do this here, 1 and minus 1, and then we could evaluate either one to get the points. The points are minus 1, 1, and 1, 1. And if we sketch it, maybe I'll sketch it here and then set up the integral here. We can sketch this. Oh, let's see, I need to have a minus 1. What happened to my eraser? Put it over here. Maybe I'll make it here and here, and they intersect at here, 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 and here. Okay? And then one of them is x squared. That's pretty easy to draw. It's going to be concave up, go through the origin, okay? More or less. One of them is 2 minus x squared. So this, let's see, I'll label it. This is x squared. Then we have 2 minus x squared, which will be concave down. It'll go through the point 0, 2. And then it's going to come down like this. So I have a plate here in this region. Okay, and this is minus 1, and this is 1. Well, now we can just set up the integral and be done. This really isn't too hard of a problem, especially because we don't have to integrate. We set up the integral. It goes from minus 1 to 1. Then we need density, which is 3 to the x. Okay? Then we need, let me label. This one was y equals 2 minus x squared. So then, sorry about that. We need upper minus lower. So this would be 2 minus x squared minus another x squared. This is upper minus lower, and then dx. And all you can really do here to simplify some is just add minus 1 to 1, 3 to the x, and then we have 2 minus 2x squared dx. So this would be the final integral, okay? We certainly could integrate that. It's not too bad. This is an exponential. Well, here, this is algebraic. We could work by parts. We'd have to do it twice because we have a squared power, but in principle, we could do that. But the problem didn't ask it, so I will stop here. Okay, so now I want to do one where we are going to integrate. We'll do the full problem. This one's fun. It involves trigonometry, which I love. And this will also be a by parts problem. So it'll be a nice exercise in integrating, not just setting up, although a lot of the applications that we are working through, what's new to us is the setup. Suppose we have a thin plate occupies a region bound by the following curves, bound by the cosine, the sine, and then we will look between 0 and pi over 4. And then this plate has density function delta of x is x, and we want to find the mass. Of the plate. Okay, here we go. Well, the first thing is, let's graph it. I could set the two curves equal and things like this, but I don't really need to because I know my x values. It goes between 0 and pi over 4. And then I know my two curves. So I just need to graph the cosine, graph the sine between 0 and pi over 4, and I will know how to set up my integral appropriately. Let's see. I will do pi over 2. Pi over 4 is halfway, and these both go between 1 minus 1. The cosine, I'll start with the sine. Sine goes 0 high, and then it will go 0 high, 0 low, 0, but I'm not needing all the way to 2 pi because I'm only looking 0 to pi over 4. So the sine will be something like this, 0 high. And the cosine, it says high, 0, low, 0, high. So here, the cosine will start up here, high, 0, low, 0, high. I just need, on this first part, high, 0. And in fact, we know they're going to intersect at pi over 4 because the sine and the cosine are equal. This y value is root 2 over 2, okay? Maybe not the best in my picture, but we know that's the case. The sine and the cosine are equal at pi over 4. My region, or I should say my plate, it occupies, well, yeah, this region. So my plate is in green. And we see, maybe I should label, the cosine is here. Okay, find the mass of the plate. We have our picture. Wonderful. Now, this will be, let's set it up, but I'm going to do more than that. We will do the whole integral. The setup is we integrate 0 to pi over 4, and then we have x. That's our density. Then we have to do upper minus lower. Upper is the cosine. So it's cosine x minus sine x dx. Okay? If this was a setup only, we'd be done, but then we'd be missing a lot of fun of this problem. So we're going to keep going and finish it. Now, if you see algebraic trigonometry, it's not an obvious substitution, like if we had cosine of parentheses x squared, and an x out in front, substitution. But we don't see that, so this is by parts. And if you remember this, Liate, this is the order in which we search for u. We do not have a log or inverse trig. We have algebraic. Algebraic. Okay, so maybe I will come down here. Let's put a little like this. Come down here and try to do the indefinite interval. Maybe I need a little more space. And then once I have that, I will go back here. Or, yeah, that sounds good. Okay. Okay, so if we do the indefinite interval, we have u is x, dv, which is the trig part, is, well, it's everything else. So it's cosine x minus sine x dx, parentheses. Okay, du is dx, and then v is, well, we have to integrate. When we integrate cosine, we get positive sine. Then we integrate negative, well, the integral of sine is negative cosine. We have this, so it's going to be a plus cosine. So we have sine x plus cosine x. And then it says uv minus the integral of v du. So we're going to have x sine x plus cosine x minus the integral sine x plus cosine x dx. Now, I can integrate this too, right? Okay, perfect. This is equal to x. Again, we have sine x plus cosine x. And now when I integrate, I'll put the minus. Okay, you integrate sine, negative cosine. As I was saying, you integrate cosine, positive sine. So now, okay, we would need a plus c. I'm going to jump into the definite once I get this antiderivative. My final answer, what can I combine? I have x plus 1 cosine x. And then I have x minus 1 sine x. So here is, maybe I shouldn't underline it, it looks like an answer. This would be an indefinite integral for this integrand. Now let's use it here because I need to evaluate. Okay, so this part equals, I have x plus 1 cosine x plus x minus 1 sine x. And then I evaluate all of this between 0 and pi over 4. Okay? Well, fine. We have pi over 4 plus 1 times square root 2 over 2. Then we have pi over 4 minus 1 times square root 2 over 2. And now we subtract, evaluating at 0, but let's see. Well, we can look at our picture. The sign of 0 is 0, so when I evaluate this second term here at 0, 0. So I just need to subtract off this first term. It's going to be minus, well, put in 0, we get 1 times 1. Okay. And now I can simplify this slightly, right? Oh, because I have a plus 1 square root 2 over 2, a minus 1 square root 2 over 2, then I have 2 pi over 4. So this is going to be pi over 2 square root 2 over 2 minus 1, or we have pi over 4 times square root 2 minus 1, okay? This would be the mass of the plate. Now, oh, okay, I got the same answer. I'm always worried that I make a mistake and I don't have you all to tell me that it's wrong. So I checked my notes, but I got the same thing in my notes. So this is the mass of this plate.